Hello everyone, welcome to this course Digital Electronics and Circuits, and in this particular lecture we will be talking about combinational circuits, and mostly we would be focusing on adder and subtractor circuits. And when we talk about addition, right, we will be beginning with basic addition of binary numbers, right? We will do a binary number addition. Then we will talk about half adders. We will extend the concept from half adders. We will talk about full adders. Then we will talk about 4-bit adders, and then we will talk about few subtractors also, right? We will subtraction we will perform, and we will create a circuit for performing a subtraction, right? So 4-bit subtraction. Okay, so let's get started. We have a lot to cover in this particular lecture. So when we talk about binary addition, right, the basic general rules of binary addition are these. So basically, if we have two numbers, right, A and B, so 0 added to 0 is 0, 0 added to 1 is same as 1 added to 0, which is equal to 0, and 1 added with 1 is nothing but 0 with a carry 1. So this is sum, this is carry. So basically, if we assume, let's assume we have like a 1-bit unsigned, right, 1-bit unsigned integer. So basically we will say 1 plus 1 in decimal should be equal to 2 in decimal, right? So basically if we say that, okay, 1 in decimal is 1 in binary plus 1 in binary, we say that this is equal to 1 and 0 in binary. In unsigned nomenclature, this will be equal to 1 into 2 raised to power 1 plus 0 into 2 raised to power 0. Recall this from our first lecture. This is 2 plus 0, which is equal to 2, right? So as a thumb rule, right, the basics of binary addition is a number added to 0, 0 added with 0 is 0, 0 added with 1 is 1, which is same as 1 added to 0, and 1 plus 1 is 0 with a carry 1, correct? So now let's look at two numbers, right, and we try to add two numbers. Let's assume that we have a number, say 1 0 1 0, and we have another number, say 1 1 1 and 1, right? So basically this is called augend in a general addition term, right? This is called addend. Now if we add both of these together, 0 plus 1 is 1, 1 plus 1 is 0 with a carry 1, so this we denote using a carry in, right? So and then 1 plus 0 is 1, 1 plus 1 is 0 again with a carry 1, 1 plus 1 is 0 with a carry 1, and again, right? So basically it will be 0 with a carry 1, 0 plus 1 is 1, this will be 1 with a carry 1. So this is nothing but sum. If you see over here, what we have is, we have a result of two additions as a third number, and basically this is something which we called as LSB, which is nothing but least significant bit, and this is called MSB, which is the most significant bit, right? Most significant bit. Now if we try to do this thing, like let's assume we are talking about unsigned numbers only. What is this number, right? Let's try to do it in terms of decimal. Let's try to prove, take a proof that whether what we have done is correct or not. If this is an unsigned integer, what is this particular number? This is nothing but 1 into 2 raised to power 3 plus 1 into 2 raised to power 1, which is nothing but 10. What is this? This is 1 into 2 raised to power 3 plus 2 raised to power 2 plus 2 raised to power 1 plus 2 raised to power 0. This is 8 plus 4 12 plus 14 15. So sum of it should be 25. And what is our output? Our output is 11001 in binary, would be equal to 1 into 2 raised to power 4 plus 1 into 2 raised to power 3 plus 1 into 2 raised to power 0, which will be equal to 16 plus 8 plus 1, which will be equal to 25. So this tells us that our addition is correct, right? So basically we took an example of both the numbers being unsigned numbers, and we know one thing which we spoke in one of our lectures is when we have 4-bit number. So let's assume we have like a unsigned representation, and then we have a signed representation, right? And let's assume that we have a 4 bit, 3 bit number, right? So how many possible combinations are there for unsigned numbers? We will have value from 0 to 7, right? And for signed number, we will have representations from -4 to 3. Similarly, if we have a 4-bit number, unsigned values can have values from 0 to 2 raised to power 4 minus 1, which is 15. And similarly, we can have a value from -8 to +7. If we have a 5-bit number, this could be 0 to 2 raised to power 5 minus 1, which is 31. And this could be -16 to 15. And I am telling you these ranges because eventually when we do a arithmetic, when we add a positive number to a negative number, right, we need to know all these things. And if it is 6 bit, right, we for that, because we will need to figure out how many are the number of minimum bits which we could use to implement that particular circuit, right? This would be 0 to 2 raised to power 6 minus 1, which is equal to 63, and this will be -32 to +31. So I created this table just to give you an example of, let's assume we have two numbers with us and we have to add those two numbers. And let's assume we have two numbers using a sign. We have already seen multiple calculations using unsigned integers. Let's use something called signed, and let's assume we have two numbers. Say one is -14 and one is -14 and +5. So basically, let's assume we have two digits, and those two digits are something like, okay, let's assume we are having a 5-bit signed representation, right? And let's assume we have two numbers. Say we have to add 14 minus 14 with, say, 8. Now, right? So this is, we have to do this addition. So we have to add both of them, right? So basically, how would we write 8 in decimal? 8 decimal would be equal to what? 100. And since we are having -14, we need minimum 15 bits to represent this system. This will be like this, right? And how would we represent -14? So first bit will be the signed bit. So -14 in decimal is equal to, right? Correct. So basically, converting, if we have like 14 in decimal is what? Like basically it will be like, if we convert that into hexadecimal, this would be something like, we, okay, to divide this, right, we will be dividing by 2 2 3 1 2 1 1. So 14 is 110, right? So 14 in decimal is something like 0110. And if we have to convert 14 into -14, right? So we already spoke about complements, radix complement and diminished radix complement. So converting 14 into decimal to -14 is basically, we have to do take 2's complements and add 1. So 2's complement for this is what? All digits reversed, 1 0 0 0 1 plus 1. So basically, if we add this, what it will be? 0 with a carry 1 and then 1 0 0. So this will be -14 for me in the binary format. I hope this is clear, right? So how we converted 14 to, we have to add -14 decimal with 8 decimal, right, in a binary format. First of all, what we have to do is we have to convert 14 into -14. We know how 14 is 14 in decimal is equal to this particular number in binary. How did we get this? We use this particular mathematics approach where we said 2, where we 2 7 0 is a remainder, 3 is a multiplier, 1 is a remainder, then again 1 1 is a multiplier. So this we got as a number. And then to convert a positive number into negative number, what we do is, we already saw in one of our beginning lectures that we usually take 2's complement and add 1. 2's complement for this particular number would be 10001, and when we add it to 1 over here, this will be 0 with a carry 1. So this will be this particular number. Now if we add these two, right, what would be the output? 0 1 0 1 1. What does we know about this 5-bit number? We know that this is a negative number because MSB is negative. So this is a, MSB is 1, so this is a negative number. And what is the value of this negative number? If we have to convert a negative number to a positive number, right, what we would do is, to know the magnitude of this number, we know this is a negative number, but how do we calculate the magnitude? Magnitude of this number, again we have to do 2's complement and add 1. So 2's complement of this number is 0 0 1 0 1. Once we add 1 over here, it will be 0 with a carry 1 1 0 0. And this number is nothing but 5. So basically this is like minus 5. Sorry, this number is nothing but 110 is nothing but 6, because this is like 2 raised to power 2 plus 2 raised to power 1 is 6. So we were able to do a addition of two numbers, correct? So just to capture it again, so what we had to do is we had to add minus 14 with plus 8, which we know this will be minus 6 in decimal. What we did for this is we had 14 which was equal to 0 1 1 1 0 in decimal. We said our minus 14 in decimal would be 2's complement of 14 in decimal plus 1. For this what we did is we inverted every digit, added that to 1, 0 with the carry 1, 0 0 1, and then this is our number, right? This was our minus 14. So we inverted everything, and then our 8 in decimal was, when we convert that into binary, would be 0 1 0 0 0, right? Now if we add both, 0 1 0 1 1, this is our result. And how do we find the magnitude of this result? We know that this number's MSB is 1, so this is a negative number in sign representation. To find a value, what we will do is we will again do a 2's complement and add 1. So 2's complement of this particular number will be 0 0 1 0 1, and once we add 1 it will be 0 with a carry 1 1, and this number is nothing but magnitude is 6, sign is negative, so this is like result is minus 6, which is equal to 1 1 0 1 0. This is a result of binary subtraction, right? I hope this particular part is clear about binary addition and binary subtraction, because we will be, as we move ahead, right, we will be looking into something a bit complex, and this is the basics for understanding that particular part, right? Now we have spoken about binary addition, binary subtraction, right? Now let's talk about something which is called as a half adder. An important concept. This is asked in multiple interviews also, right? Because this forms a building block for all the adder modules. Half adder is nothing but, it's like a 2-bit adder, right? So it's like a 2-bit adder. So basically assume that we have a combinational circuit over here. This is like a half adder, we call it. We will have two input bits, both single bit, right? We will have a bit x, we will have a bit y, and this adder will generate a sum for us, and this will generate a carry for us, right? So this is what is called as a half adder. And now let's try to create a truth table for this half adder. Let's assume our inputs are x and y and our outputs are c and s. So input could be, possible combinations are these ones. Sum for 0 0 is 0 with a carry 0, 1 with carry 0, 1 with carry 0. Sum is 0 with a carry 1. Right? Now if we look at the this particular equation, right, and this particular truth table, how we can drive the equation of sum. Sum is nothing but odd function over here, which is equal to XOR, right? So this is like x x XOR with y. Carry is what? Carry is x into y. So using this operation, right, because this is carry, this is equal to 1, which is equal to x and y. These two are, we have already seen, this is nothing but XOR gate, which is like x bar into y plus xy bar, right? So basically what we can say over here is, we have drawn an half adder circuit where what we can do is, I have two inputs x and y, right? If I XOR these two inputs, right, I will get an operation of sum, and if I AND these two inputs, right, I get a carry. And basically if I draw a box over here, so this half adder circuit looks like something like this. We used one XOR gate plus one AND gate. So basically this is important part. Half adder, we could actually remember this. Even if we don't remember, it's fine. Sum is equal to x or y, sum is equal to x XOR y, and carry is equal to x dot y, right? Now let's move on to the next concept. Next concept is something which we call as full adder. And full adder is nothing but it's like a 3-bit adder. Half adder was 2-bit adder, full adder is a 3-bit adder. So to say, this is something like this. We have a black box circuit over here. We have three inputs. right? And we have two outputs. So three inputs are what? We have three inputs as x, y, and let's call third input as carry in. There's a reason why we call it as a carry in. We will understand it once we talk about like 4-bit adders and subtractors. Let's assume the three inputs are named as x, y, c in, and then we have outputs as sum and carry out, right? And now if we say that this is a full adder, how do we realize this full adder circuit? If we have to implement it using binary gates, how do we realize it, right? So what's the first step? The first step is like we draw a truth table for this particular logic. And truth table would be input is x, y, carry in, output is sum and carry out. So possible combinations are all zeros, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. Sum for this is 0 with a carry 0. Sum of this is 1 with carry 0, 1 with carry 0. Sum is 0, 1 is 1, 1 plus 1 is 0 with a carry 1, 1 with carry 0, 0 with carry 1, 0 with carry 1, 1 with carry 1. Right? And what do we see over here? Basically, sum is equal to summation of m, 1, 2, 4, and 7. And carry is, right? And carry is summation m, 0, 1, 2, 3, 5, 6, 7. So now if we try to create a circuit out of it, right? Do you remember something? We already spoke about a 3 input XOR gate. So basically if we try to draw a K map for sum, it will look something like this. 0, 1, 2, 3, 4, 0, 1, 2, 3, 4, 5, 6, and 7. This is like for sum. This is nothing but a odd function. And for a odd function we said like sum is equal to x XOR with y XOR with c. So it's XOR of all the three inputs, right? Whereas my carry out, if I have to look at my carry out, this is something like 0, 1, 2, 3, 0, 1, 2, 3, 4, 5, 6, 7, right? So what we can do over here is we can simply say this is like combination of x, y, and c. If you have to do a circuit minimization over here, this is 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. So basically what all possible combinations we can have? This, this, and this. So my carry out is equal to what? This particular term is what? This will be y into c. This term would be x into c plus this term would be x into y. Alright. I'm just trying to look at it again. So basically if we look at the carry out term, this will be equal to 0, 1, 0, 1, 2, 3, 5, 6, 7. 0, 1, 2, 3, 4, 5, 6, and 7. And if you see, right, this is one of the term, and there is an alternate expression for this also, which we can say simply. So the alternate expression of this is something like if we try to expand the term, right? So this is what? X bar y c in plus xy bar c in plus xy c in bar plus xy c in, right? And if we calculate this, right, if we take c in common, what is x bar y plus xy bar? This is x XOR with y. And if we take xy common from here, c plus c bar is what? A number added with its complement is always 1. So basically what we got out of here is sum is equal to x XOR y XOR c, and carry out is nothing but x XOR y into c plus x into y. So now if we have to implement this particular circuit, right, which was black box for us, what we will do is we say we take x and y as an input, we put a XOR of these together. So this is nothing but x XOR y, And for sum, what we have to do is we have to XOR it again with carry in, right? And then what we have over here is we have x and y coming out over here. We AND them. This is x and y. Alright. So basically what we will do over here is we have third input which is called carry in. If I say I have a third input called carry in over here, we take it over here. We XOR it together. This is my sum which is output. So basically this will be x XOR y XOR c in. We have xy over here, we have to OR xy with xy XOR into c in, right? So we need to have one more AND gate, right? Which we AND with c in. So basically it's ANDed with c in. And we OR with this one. So basically this is what x XOR y into c in, and then it's ORed with xy. So basically we OR it with this carry out. Right. So basically, does this circuit ring a bell? So basically, if you see over here, right, we had to draw a full adder circuit with three inputs x, y, c in, and two outputs sum and carry out. What did we get? We got a full adder circuit which is similar to x XOR y XORed with c in as sum output, which is this one, and we got a carry out as x XOR y output. We multiplied with c in, which is a third input, and we ORed it with x and y. Basically, if you look at over here, right, if I change the pen color and we do some comparison over here, right, let's call it red. What does this does this sound a bell? And this as well, right? So we have x, y, c in, output of this goes into xy, and the third input, right, which goes into this one, and what happens is x or y again into c in and in. So basically these two are nothing but our half adder with x and y as inputs. This is again a half adder with what inputs? The inputs to this half adder is x XOR y and c. Correct? So basically what we say over here is, and so basically since these are two half adders in like a serial fashion back to back, output of this half adder which is taking these inputs would be sum is equal to x or y, x or with c in, and this carry out of this half adder would be x XOR y into c in, and it eventually gets odd with xy at the end with an extra logic, right? So basically what we saw over here is our full adder, which is nothing but 3-bit adder, can be formed using two half adders plus one OR gate. And intrinsically we saw this is getting formed using one XOR gate plus one AND gate. Correct? So what I can do simply is, what I can do in such a case is I can use a half adder, two inputs, two outputs. Then I can put an again one more half adder, which I can call half adder 2, half adder 1, x as y as an input. All this sum as an output is x or y. This goes as an input to another column. And then we have the third input over here as c in. So c in goes as an input to this half adder. What we do over here is the output, right? So this is like sum and this is like carry, sum and carry. This sum is nothing but x or with y, x or with c in, and whatever carry we get over here, this is like x, x or with y into c in. What we do is we XOR, we have an extra uh, OR gate. We need to have an extra OR gate, right, which will tap this carry out, C out. This is C out to generate x XOR y c in plus x out. So what we saw over here was we looked at a 3-bit adder and we realized a 3-bit adder using a 2-bit adder. And the benefit of this particular thing is, right, if we have to draw, like for example, we drew a truth table over here for a 3-bit adder, we ended up having a 2 raised to power 3 entries. So we had to create a sum for 8 entries. Then similarly, we have to create a carry out for 8 entries as well. Whereas for 2-bit adder, right, calculation was pretty simple. We were able to have only 4 entries, and this was like calculation was very simple. And if you see, if we went for from 2-bit adder to 3-bit adder, the calculation got a bit complex, right? Now let's do one more thing. Just to understand like why this half adder or full adders are important and why did we implement a full adder using a half adder. Let's talk about a 4-bit adder. So when I say 4-bit adder, right, what would that mean? That would mean is, let's assume we have two inputs, right? A, this is one input which is 4-bit input. This is again one more 4-bit input which is, let's assume, this is similar to the expression which we saw in the beginning when we did minus 14 plus 8, right? So this simply means that we have 4 bits as an input. Let's call them A3, A2, A1, A0. And then we have again 4 bits as input. Let's call it B3, B2, B1 and B0. As the output of this, right, what we have is we have one more carry in over here. And then we have a carry out. And then we have a set of sems. S3, S2, S1, S0. So if we have having something like this, right, how do we implement it? How do we implement such a adder, right? So basically, right, first step which we have been doing all together till now. If we go by a traditional approach, we will say A3, A2, A1, A0. Then we have B3, B2, B1, B0. C in, right? And what we'll do is like we will have sum and carry out, and sum would be like something similar to this one. When we say sum would be like S3, S2, S1, S0. So now what we will do, how many possible combinations of this we will have? So we have 9 inputs. So number of possible combinations will be 2 raised to power 9. So 512 inputs. So basically what we will have to do is we have to draw a truth table with 512 entries. And after we draw 512 entries, what we have to do is we will have to calculate the circuit for 5 outputs, and 5 outputs being S3 to S0 and C out. Is this a feasible problem to solve? It becomes sort of an unbounded problem. It's still bounded, but it's like a pretty complex problem statement where we will look at 512 entries. And if you remember, right, k-maps, we will not be able to analyze it usefully using a k-map, and then we have to look at for the Queen-Mikulski method, which itself would be pretty time consuming, right? Other than this, right, can we do something other than this? So basically if I tell you, right, we have three inputs, 4-bit input A3, A2, A1, A0. Then we have a second input B3, B2, B1, B0, and then we have a carry in. Can we add them? So can we divide the problem statement to a smaller portion? What does this look like? If we just look at this particular thing, is it like a 3-bit adder? Once we add this, we will have some result S0, then we will have a C in 1. Again, once we add, we will have something like S1, then we will have C in 2. This will be S2, then again we will have something like C in 3. This will be S3, and then output will be C out, right? So can we implement a 4-bit adder? We have two numbers which are 4-bit long using a 3-bit adder. Yes, we can do it, right? And once we have to do it, right, what we will do simply is we try to use simple full adders which we devised just now, right? How did we devise a full adder? Using two half adders, and let's call that block as a full adder block, right? So basically what we would say is, let's assume we have a full adder over here. We have a full adder. We have already looked at this circuit. We have already realized this circuit using two AND gates, two OR gates, and one two XOR gates, two AND gates, and one OR gate, right? So let's assume what I say is we have this, what we saw is this adder has some input, say x and y, right? This had an sum as an output, this has an carry in as an input, and then this has an carry out as an output, correct? So basically, okay, let's draw it a bit clearer because this is important. Okay, let's assume we have a full adder over here, and this full adder has two inputs x, y. It has a sum which is output. It had a carry in, which is this port, and it had a carry out. We have already realized this full adder circuit using two half adders plus one OR gate, right? Now let's assume that we input like A0 here, B0 here, C in here. What would this give me? This will give me S sum out with a carry intermediate, right? Intermediate carry in 1. Now let's assume that I cascade one more full adder over here, where this C in 1 goes to C in port. Sum will give me S1, which I show over here. We have X and Y port, which are connected to A1 and P1 respectively. And then we again have a C out of full adder, which is having carry in 2 and 3. This again goes to again one more full adder, where sum becomes S2. We have a carry out, which is nothing but C in 3, and then we have X and Y as an input. This is nothing but A2 and B2. And then similarly what we do over here is we have a third full adder, where the C in goes to C in. It's again C in. C out is nothing but my carry out over here, final carry out. This particular X and Y would be nothing but A3 and B3. This will be S2, S3, sorry. Will this circuit work? So basically, if we say we had A0 and B0 C in, this is a low, the LSB least significant bit. These are 3-bit adders. We used a full adder to add these 3 bits. I generated a sum and a carry. Again, when we generated a carry, we had 3 set of inputs going on to a next full adder, followed by next full adder, followed by next full adder. And at the end, we will have like S0, S1, S2, S3 and carry out. So basically what we did over here is we used a full adder, right, which was easier to derive and which we implemented using set of two half adders as well plus one OR gate. We used four full adders, right? We used four full adders to do a addition like this. Was this better than doing a K map for 5 outputs like C out, S0, S1, S2, S3 and looking at a like a 5 well entries? This was much easier, right? So that's why half adder and full adders are very important, and it's not only because of these two, right? Let's assume that tomorrow if we have to add two 4-bit numbers now, right? Now let's assume that we have like this 4-bit adders. Now let's assume that this is nothing but we have a 4-bit adder now, right? So let's assume that tomorrow what we have to do is we have to add two numbers which are like 8-bit, right? So let's assume that tomorrow we have a problem statement where we have A0 to A7, 8-bit number, B0 to B7, two numbers. Then what we can use is we can simply use two 4-bit adders to get an 8-bit adders, right? And that is all about this particular design, correct? Here we spoke about adders. How about subtractors now? Subtractors we will be talking in the next lecture.